So welcome to part 2 of our lecture. So right now we're kind of looking at the generalized eigenspace of G20, and what we're trying to do is we're trying to find a nice basis for of the generalized eigenspace of the eigenvalue 20. Now, if you remember from the actual proof that we discussed in lecture 25, the way that we do it is in some ways we kind of build up backwards. We start with a basis for here, then we use that to build a basis for here, and then we start with a basis from here. But the way that we're going to go about that is we're going to just start with a basis of G, the generalized eigenspace. We use that to build a basis here, and then we kind of go backwards and find a basis, a new basis from G20. So let me kind of illustrate what we're doing there. Okay, so first of all, a basis for the generalized eigenspace is just the null space of this operator, and that was written very poorly, so let me kind of clean that up. All right, so this is equal to the null space of t minus 20I cubed. Okay, so that's what it equal to. And you can turn this into the matrix, right? So this is, you could look at the matrix associated to the third power of this matrix, and you're asking for the null space. So this is really a question from Math 1B03 of finding the basis for the null space. I've actually written it all out here. And just to kind of keep our notation nice here, I'll just let U1, U2, and U3 denote these specific vectors. Okay, so U1, U2, 3 is a basis for the green box. Okay, so now how do we find a basis for the range? Well, the basis of the range is given by the linear independent elements in the following set, right? So what you do is you apply the matrix of M t minus 20I, and you evaluate it at each of these vectors. All right, so each of these vectors here get bumped into the range. They actually form a spanning set, but it may not be a linearly independent set. So we know from way back in chapter 2 and 3 that once you have a spanning set, you can just trim out the linearly independent elements and you get a basis. So you have these elements right here, but these guys are not linearly independent, because if I take the first element and I subtract the second element, I get the third element. So the third element is kind of redundant. So the basis for the range can be written in terms of the first two vectors, right? So 4, 10, 4, negative 10, and 5, 5, 5, and negative 5. Okay, so there we go. Let's see what I've written up here, if I have enough room, or I can squeeze it into the bottom here. Okay, oh, I actually rewrote it here. And let's say we call this the span of W1 and W2. Okay, and now we want to do the same thing. We want to find a basis for the range of t minus 20I squared, and it's given by the linear independent elements of applying our operators to W1 and W2. Okay, and so I do that. So I take the matrix associated to this and I multiply it by the first vector and I get this. And if I took the second vector and I multiply it by the matrix, I get 0, 0, 0. And then I'm asking for the linear independent elements, which is just the first vector. And you can actually kind of rescale it. We don't need all those 30s, right? You could just take 1, 1, 1, negative 1. Okay, so just to kind of recap, what we have here is we found a basis for the whole thing. Then we use that to find a basis for the range, and then we use that basis to find a basis for the range of t minus 20 squared. And that's as far as down as we have to go. Now, in a general situation, you may have to keep going all the way down until you get to the last case where the range is non-zero. Okay, so now we have that, and now what we want to do is pull this basis back up. Okay, so we're starting here, and now we want to pull it back up and get a different basis for the range of t minus 20I. So first of all, what we want to do is find an element in the range of t minus 20I that maps to our basis element. Okay, so 1, 1, 1, negative 1, right, going back to my picture, is in here, and we're asking which thing maps to here. and there has to be something because we're mapping into the range. Okay, so we have to solve this equation, and this is just kind of, you know, week 2 stuff of linear algebra, your first linear algebra class. The vector is 1/5, 0, 1/5, and 0. Okay, so just take any vector that maps to it. There could be a family of things, but just take one vector that maps to it. So that's one of them. Okay, and now notice that this vector is in the range. That's how it's defined, right? It's actually the basis for the range of the space, and that's contained inside of the range of t minus 20i. And this new vector is also in the range of t minus 20i, and we'll use this as the beginning of a basis. Okay, so we'll use this, and we want to use this to build the basis of the next space that we're working on. And that doesn't look, it's not the range, it's the range. Okay, we're not being angry here. Okay, we're looking at the range. Okay, now, in some sense, if you look at these, it's pretty clear that they're linearly independent. And in our case, the range is, the dimension of the range is 2. So we actually have a basis. In some sense, this is the basis. Okay. And so our vectors are a basis for the range of t minus 20i, okay, because they are linearly independent. Because they are linearly independent. Oh, too many independent, too many D's in there. Let's fix that up. Okay, there we go. So there's too many that are linearly independent. Now, this is where the kind of this algorithm gets a little tricky here, right? So if this had not been a basis, okay, it could have been that this range was much bigger. Then we would actually have to extend by linearly independent elements to get a basis of the range of t minus id, depending upon which d we're working on. And then this has to have the property that each of these new basis elements are mapped to 0 by this operator. So I'll talk about that a little bit at the end. But this is where it comes a little tricky when you're doing these calculations, that sometimes things don't work out too nicely for ourselves. Okay, and now step 3 is we want to pull back our basis that we have for range t minus 20i to the basis of the generalized eigenspace. And so this was the new guy that we had introduced at the previous stage. And so we just want to solve this equation. Okay, so we're asking what thing gets mapped to this. And that the thing that gets mapped to this, right? We're just solving this system of equations, and using your linear algebra skills, you have that the solution to this is 17/300ths, 1/300ths, 30ths, 2/30ths, and 0. Okay, so that would be my vector x1, x2, x3, and x4. Okay, and so what we have now is all of these vectors are linearly independent in our generalized eigenspace. Okay, and since the dimension of our generalized eigenspace is 3, right, they form a base, they give us the basis. So this is a basis for the generalized eigenspace. Okay, so we'll pause here. I just don't want my videos to become too long, and we'll kind of like summarize kind of what we've done so far. Okay.